Hey everyone, so today I'm going to be taking you through how to make a basic model in OpenSees, do an analysis, and then get the outputs from your model. The example I want to take a look at is this truss. This is off the OpenSees Wikipedia, and so I'm going to go through things assuming that you know almost nothing about Python or OpenSees. You can see that they actually give an example of how to create the model. They show you the code down here. So what I want to do is take a look at some of this code and kind of give an explanation for why they're doing some of the things that you're doing. But I highly recommend that you kind of go through this code on your own at some point. And then a resource that I'm also going to be using is, this is the same example just done in Python. So we're going to be taking a look. I'm going to be being pretty lazy and copying and pasting code from here for brevity. So let's get into things without any further ado. I'm going to be using Spider as the editor of choice. I really like Spider because I think it's pretty easy to just jump into and start coding. So what I recommend that you do is actually make a project for this example. So generally you wouldn't have to do something like this. Like if you wanted to just create a file and get into coding, you could totally do that. I think it's just good practice to get in the habit of building a project and lumping all the files that are associated with an analysis in that project. It'll just help you in the long run if you have these good habits. And so I think I'll do a quick sketch of what the program structure is going to look like. It's going to be a little bit different than what they're doing over here. So taking a look at the model, this is what we're going to be creating. You'll note that the units are in imperial. And whenever you have some sort of finite element model that you want to create, it's really important to use consistent units. So I'm going to be converting all these into metric when I do mine. I'm also going to be kind of parameterizing things as variables. If you note, when they issue their commands to create nodes, they're kind of just putting the numbers in to the function directly. And then I think that's not really super good practice. So we'll be creating variables for our file. So jumping over, the structure is going to look something like this. I'm going to have a section for units. This is going to be variables, input variables. And then I'm going to have a section for my actual OpenSees code. OpenSees analysis. Okay, great. And of course, the first step that you would always have to take when you're using Python is you're going to have to import the module that you're using. So let's do that. Import OpenSees py.opensees, and I'm going to import it as OP. If we look at the example that they have, they import it as star. You're totally welcome to do this as well. I like importing it as something. If I find it just a little bit cleaner, but this of course is a valid way of doing things. So let's actually get started with the unit conversions. I mentioned this because this is like a cute little trick that I do all the time. I actually define variables for my units. So we'll say meters equals 1, newtons equals 1, pascals equals 1. And then I can actually define my unit conversions in terms of these. So let's do that right now. Say inches equals meters. Okay, feet equals 12 inches. What else? Kips? Yeah, kips. Kip equals 4.45 times 10 to the power of 3. newtons, and KSI 6.89. Yeah, power 6 times pascals. And then, so yeah, let's now do our like pre-processing, or rather variable like inputs. So obviously we're going to need the geometric information of everything. Like for node 1, we need like the XY coordinate. Same for all our nodes. And then it'll be nice if we have all this kind of defined in one place at the start of our file. You'll note when you look at this truss example, say you wanted to change like the area of the element and the node, like the x coordinate of one of your nodes. That would be kind of awkward because we'd have to go through, we'd have to like, okay, look, our nodes are here, change this, then we'd have to go find our elements, change like the area. It's just not as clean. So it's nice if you have it all in the same spot. And so let's define our variables starting with the coordinates of the nodes. So I'll just use a very simple way of doing this. For each node, I'll say like x1, that'll be the x coordinate. y1 will be the y coordinate of node 1. So if we look here, 0, 0, we'll just say 0, 0. And we'll copy paste that. We'll copy paste that better. Okay. All right. So these will be our nodes. We'll just change that, the names. So now we can just input all the relevant information. So this start of 2, y coordinate is 0, and x coordinate is 12 multiplied by feet. So I think that's kind of the convenient part of having like the unit conversions. Obviously you could just like put it in your calculator, but this is super clean and very readable. So if you did it like by calculator, you have to worry about all the rounding and stuff like that. Not as fun. So let's take a look. Node 3, that is at 14 times feet. Also at 0, and then node 4 is at 8, 6. And 8. Okay, perfect. So we have our XY coordinates for each node. Now let's get the areas in there. Area 1 equals, what was it, 10? Yeah, 10 inches squared. Area 2 equals 5 squared. And then, let's see, E is 3000 KSI. And what else? Yeah, loads. Okay, so we'll say px is equal to 100 times kips. Yeah. Py equals negative 50 times kip. Oops. Okay, there we go. So now we have all our variables defined in one section. So that's really nice. If we want to change anything, we know exactly where everything's defined, so we don't have to hunt around for that. And you will note that I have, instead of putting this as just 0, I put the decimal place here. And that's the reason I'm doing that is because OpenSees expects when you pass like a variable, or when you pass data to OpenSees, it expects it in a certain type. So actually for the node commands, which we'll be using later, those want the XY coordinates to be in type float. So if you define it just as 0, it's going to think it's an integer and it's going to get mad at you. So just know that you have to be pretty careful with your dimensions. If you pass an integer, it won't be okay with that if it wants like a floating point number. Okay. So let's just take a look. Now we're ready to get into the OpenSees code. So I'll kind of pull this up and be a little bit lazy. We'll copy and paste stuff in. First command is the wipe command. This is important for reasons that I'll get into in a little bit once we can run a few commands going. But basically what this does, and I'll copy the comment, is it removes the existing model exactly like it says. And so the next is the model builder. Copy that in. You will really never use anything other than the basic model builder. So you'll always have this string here. The next string is the number of dimensions. So in this case, we have 2. Our structure is 2D. And we're actually going to put 3 here instead of the 2 that they're using. You could use 2, this is degrees of freedom. So you could use 2 over here instead of 3. This is a convention thing for me. I like always having either, for like a 2D system, I want to have 3 degrees of freedom. And for a 3D system, I want to have 6. I just trust myself to interpret like my model better that way. If I know every single model is always going to have like the same convention, it will make my life easier. So if I'm stepping into a model, I know what's going on. But just so you know, the reason why they're using 2 is because they're actually forgetting about the rotational degree of freedom because it's a truss. And so I think the next step is actually, I want to do the material before we do the nodes. And this is another convention thing. I typically like to have my materials defined before my nodes. I find that it just makes things a little bit easier to keep track of. And if you're if you have a function that defines your model, it's a little bit nicer to have the materials at the start of that than define the nodes later. That's just my preference. So, and we're going to use E because we've defined E up here. So to give you an understanding of what's going on with the uniaxial command, and I'll copy the comment as well, is this uniaxial command takes some sort of string which specifies the material type. So we tell OpenSees, okay, we want to make a uniaxial material. It's going to be of this type. Then we have this unique identifier. So the next one over is going to be the material tag. And for this, you can think of it as like the name of the material. You can use whatever you want. Because it's our first material, that doesn't mean we have to use 1. We could call this like material 1000. And so you can kind of use this to keep track of things in a creative way if you want to. Like let's say you have a model that has like steel material in it and also concrete material. You could say like all materials of like type 20 are concrete materials. And that might just make your life a little bit easier. So when you're going through and you're like checking your model, you can see like if you've defined an element and it's using material like type 20, you know it's concrete. It's just a little bit nicer, I think. But for us, if we look at our model, you only have the 1 material in here. So let's just leave it like that. And now I'm going to show you kind of the importance of this wipe command over here. So, I'm just going to restart my kernel. So one thing to note about the OpenSees model is when you create a model, it will actually remain in your kernel, in like the Python kernel, until you tell OpenSees to remove that. And so I just want to show you what would happen if we don't have this remove existing model at the start. And we ran our analysis multiple times. So the first time we run it, we get no problems. Great. However, the second time we run it, we end up with this error. And the reason why we get this is because the OpenSees model it's between runs, it's still there. So when you try and add this material again, OpenSees gets upset because there already exists a material with tag 1 from the first run that we did up here. So it's typically good practice to have this wipe at the beginning. So we remove the existing model, then we don't have to worry about getting these errors. But I think it's good to keep in mind that your model actually will be persistent as long as Python is running or you clear it. So we could actually do something like this. If we were to say to run our model now, oops, let's clear it. Great. And then let's say we want to issue a command to our model. We could actually do something like this. So I, of course, would need to change, if I want to add like a new material to the existing model for some reason without clearing it, I could give it this command and it will actually add this to the model. So now you would have a model with this elastic material called 1 and this new elastic material with exactly the same properties called 2. But so just something to keep in mind, that the model is actually persistent. Okay, so let's get back to things. We want to add as a next step, we want to add nodes to our model. So I'll just copy this. So with the node command, we have, first part to it is the tag. So similar to the material tag, our nodes each have a tag, and you can get creative with how you name nodes as well, for clarity's sake. And I'll just change this to the name of the variables that we defined above. Okay, x2, perfect. And I'll change this, are the variables. So you can see this process, oh, oops, I messed that up. Should be y, yeah, there we go. So you can see with the variables, it's kind of awkward to do this. So it can be nicer to use vectors to define the variables. And in the future, I'll show you how to do that. But I think for our example, I just want to keep things pretty simple. But if we had, say, defined these variables with a vector instead, then when we created all the nodes, we could do that just with like some for loop. And that might save us a lot of typing. Okay, so we have the nodes in the model. And just so you know, I have a lot of experience with OpenSees, so I know for the most part with like fairly common commands like this node, I know what it takes, like what arguments it takes. But if you don't know that, you would have to find that out, and the way you would find that out is using like the OpenSees Wikipedia. So we'd go over here, we'd look for like the node command, we would see what it has, what it takes as arguments, and we would input that. But so I'm going through this like fairly quickly just because I kind of have experience, but for yourself, you'll probably have to go through and check over here quite a bit. Okay, so the next step, boundary conditions, I'll just copy this in. So we're fixing the nodes. However, this is going to be a little bit different from what they're doing because I have chosen to use 3 degrees of freedom instead of 2. We also have to fix this rotational degree of freedom here. And that might seem a little bit weird because if you think of like a truss, this node right here, we typically will think of this as being free in rotation. So it seems a little bit strange to fix it. The reason why we do it like this is because whenever you have a truss, OpenSees actually handles the fact that this is free in rotation, it handles that with the truss element itself. So we actually have to, if we're using a truss element, you actually have to fix these nodes for rotation. And like I said, if you're using 2 degrees of freedom, that wouldn't be the case. But because I chose to use 3, and if you have any sort of systems with like beams in it as well, you would have to use 3. So just know that if you had like a truss, you have to fix that rotational degree of freedom as well. So to walk you through the fix command, the first part of this specifies the node that we want to fix. So fix 1, we're saying fix the first node. And then each of these next parts corresponds to the degree of freedom that we're fixing. So 1 corresponds to it being fixed. If this was a 0, that would correspond to it being released. So if we look over here, we want to have this first node fixed in the X, the Y, and we actually also want to fix it in rotation because the truss is going to handle the release. So I'll just copy that in. We'll do that 3 times. So change this. So we want to fix node 2, node 3, and we actually want to fix node 4 as well. This seems a little bit strange. We're only going to fix it in rotation. And again, that's just because the truss is handling the rotation. But if we didn't fix this node 4, we would actually end up getting an error at runtime. So just be conscious of that. It can be a little bit tricky to work with trusses. This was something that took me a while to figure out. Okay, so going back, we've fixed our nodes. Now we're going to define the elements. And a little bit of a trick that I would suggest doing is, it's actually kind of nice if we go into the OpenSees Wikipedia and we go to the elements and we copy this. It's nice to actually have this kind of above but commented out. That way we can see what the truss takes as an input, like what the truss command takes as an input, without kind of having to jump around too much. Like say you were to come back to this analysis in like a month's time, you don't really want to have to go back to like the OpenSees Wikipedia and like figure out what this random string of numbers means. It's nice to have this above so you can really quickly check what it takes. So we can see for the truss element, the first is the element name. Like the material, we can get kind of creative with how we name that. The next is going to be the nodes that it goes between. So in this case, we can see for our element over here, element 1 is going to go between node 1 and node 4. So hence the next number, node 1 and 4. The next bit it takes is the area. So let's say A1. And the material tag. So that tells you what material to use. We're just using material 1 as well. So do it like that. Actually get rid of these. Copy that. Okay. So the next one is going from 2 to 4. 3 to 4, and also we need to change our areas. What don't you like? Oh, yeah. This is A2. Perfect. Okay, so now we have our elements. The next step is going to be to define the loads. So I'll give you a little bit of information about how, like, the hierarchy of loads in OpenSees. So you start, loads get grouped into patterns, fairly simple, and then time series tell patterns how to change as we go from step to step. So if you have, like, say a bunch of gravity loads, obviously you might want to put those in like a case that has all the same properties. So that way, if we wanted to say scale all the gravity loads of our structure, we could really do so. We could do so quite easily just by scaling this number, or excuse me, scaling like the pattern. And then of course time series will tell the pattern. Like if you have like a lateral load, you might want to have that change over time. If you have like an earthquake load, the time series is going to tell the earthquake load how to change over time. So yeah, let's just copy these bad boys in. So in this case, they create like a linear time series. So this is saying that as we go from step to step, this load, like everything that's assigned to this linear material, is going to change linearly, obviously. And we're calling it 1. So each time series gets a tag. And then load pattern. So the load pattern gets a tag itself, and we assign it to the time series. So we're saying that this load pattern 1 is assigned to time series 1. And then once we finally get the node, this is a little tricky. The way that OpenSees collects loads is basically once you call a pattern, all of the next loads will be assigned to that pattern. So let's say I had 2 load patterns and I wanted to create like a bunch of loads at node 4. All of these loads will be assigned to this pattern. However, if I had it like, let's say I had a second load pattern like this, these loads would be assigned to this new load pattern. So this can be a little bit tricky. You kind of have to keep track of where you're putting your loads in. I'm not such a huge fan of this, but I mean, it works as long as you are careful with how you define things. So anyways, we're putting the load at the node, so node 4 in this case, and then we're gonna use our px and py, and because we have 3 degrees of freedom, we're also gonna put 0 in the third spot, and that's just because we have no rotational load there. Okay, so that is our loads. The next step is the analysis generation. But I think before that, I will show you how to define a recorder for our loads. Typically, I do this before the analysis generation starts. Doesn't really, as long as you do it before the first analyze command, obviously, then that's fine. But so in order to actually get information from OpenSees, we have to tell OpenSees what we want to record. So I'm going to create a recorder using the recorder command. And if you take a look at the OpenSees Wikipedia, look at output commands, we can see the recorder right here. It's a little bit tricky, I think, when you're jumping into things to understand what you can and can't tell OpenSees to record, especially when you're dealing with elements. That can be, it's a little bit tricky. Anyways, so I'm actually just going to copy and paste some pre-existing recorders that I have. We have a node recorder and we have a reaction recorder. So what this is doing, I'll try and make sense of this massive pile of crap over here. So basically we need to tell the recorder what to record. We're telling it nodes. We're telling it save it into a file with this file name as output. We're telling it to record over all time. Basically, you can actually tell it to record between certain periods of time if you want to for some reason. And then we're telling it to record a node. We're telling it node 4, and we're telling it these degrees of freedom, and then finally the displacement. Similarly over here, telling it to record reactions, and we're recording the reactions of nodes 1, 2, and 3. What else might we want to record? I think, let's see. Oh, they they just use these output commands. I think I have another element recorder over here. Yeah. So let's use this. Elements.out. So here I'm actually recording the element forces. And it seems ridiculous that you have to do this, but I would highly recommend that you have like some file somewhere that has like a list of all of the successful recorders that you've used, because sometimes you'll be reading through OpenSees documentation and it will tell you that a certain recorder type will work when in reality it's not working anymore. And finding out which ones do and don't work, there basically are no resources for that. So for your sake, I would just keep, like, if you're playing around with recorders and you're getting them to work properly, for more advanced recorders, I would keep a file that actually has what recorders have worked for you. That's what I have. Okay, so perfect. We have recorders. So record results, and then finally, this is the analysis portion. This section, I'll quickly kind of describe what's going on with these guys. For most of your basic analyses, you're not going to have to worry too much about what's going on here. So this is a command that basically creates the system of equations, and it says, I believe it says how they're stored in the matrix. This is how they're numbered, the degree of freedom numberer. This is how the constraints are handled. So if you think of like when we added our fixed constraints up here, how OpenSees numerically handles that, you can kind of change. There's a few different ways of doing that. This is the integrator type. You might mess around with this. Load control basically means that we look at the, like, as we go to step to step, we're looking at the loads to change those steps. Algorithm, they're using a linear algorithm. I'm going to change this to Newton. It doesn't matter because we're looking at a linear example, but Newton is what you're going to be using for like the majority of your analyses. And then we have an analysis object. So as you probably know, there's different types of analyses. You can do like a dynamic analysis where we consider like the accelerations of masses. This is obviously a static analysis, so we don't need to worry about that. And then we have, oh no, okay, yeah. We have this analyze command. So what this command does is it actually tells OpenSees to analyze, and it tells it to do it like a certain amount of times. I'm actually going to say, I'm going to do it like this. I'm going to say OK equals OpenSees analyze. So we're just telling it to analyze once. But the reason why you might do this is that this actually will return a flag that tells you whether it was successful or not. If it works, analyze returns 0. So we can kind of use that when we're doing our analyses to say impose a condition mid-analysis. So we can kind of check, we could say, oh hey, if our analysis fails, maybe let's change something up here and try again. So yeah, so that's why I'm assigning it to OK. So this will just tell us the status of our analyses. Anything else? Okay, the last thing we need to do is we actually need to clear our model with this wipe command. Okay, so I'm just going to save this. Basic truss. And so I'll show you what happens if we don't if we don't use this wipe command. And if I just try to run my analysis, yeah, oops. So I actually, you may have noticed, I forgot to uncomment this wipe command, so that kind of messed things up when we tried to run our analysis. Also, I've made a mistake here. When I copy and pasted my truss command, I forgot to change the tags of them. So we should be good to go now. Yeah, perfect. So you'll see we run our analysis and we get these output files. So if I go and take a look, however, they will be completely empty. And that's because OpenSees has to close the file. So the way we can do that is by removing the model again. That will actually allow OpenSees to close the file. And then if we go to the Truss example, yep, we can see that we have the data. Oh my goodness. We have the data of our analysis in these files. So like I said, this is node 1. This is saying at time step 1, X deformation, Y deformation, and rotation at that node. So I'll just quickly show you what actually would be kind of nice is if we did this op.initialize, and if I can spell, please autocomplete. No, initialize. Yes. Okay. So we do this initialize command, and now if I run it again, I'll just show you the results, reload them. We have this nice starting point, and if so we'll start at 0 with 0, and then we can see the first time step will be the first load that's in there. And then the other thing we can do is, let's say we want to analyze this like 10 times. We can actually just put 10 in here, and then that will tell it to do 10 steps. So if we think of like the load that's being applied, this like 100 kip load is going to be applied 10 times. So if we run it, take a look at our results, we can see, okay, yeah, we have each of these 10 analyses. And then I think that's where I'll end it. There are some more complicated things that you can do. Like typically it's better to do this analysis with like a for loop instead of giving it 10. But I think I'm going to save that for another video.